All right, so just a quick agenda for the Tech Talk today. We have an application overview talking about what end-use parts are, what considered to be, where they actually fit. We're going to do a process comparison, looking at the traditional manufacturing, and then looking at FDM, so fused deposition modeling. I'll go over what that is and then how that could fit or possibly replace those traditional manufacturing methods. Then at the end, we have some benefits of FDM, and then a customer success story. And throughout my presentation, we have all these pictures, and a lot of them, probably all of them, have some sort of 3D printing involved, some FDM involved. And if I know the story behind it, I want to share it. I had lots of good comments last Tech Talk, and that was the favorite part for some people, is the applications that we showed or where they were used at. The left side here, we see these tan parts. These are actually replacement parts for an old Boeing airplane, where Boeing isn't going to manufacture these anymore. It's actually a little vent that you use to control the airflow. They're not going to manufacture it anymore. They're not going to tool it for it. There's not enough of them to make it. But now there's all these third parties coming along and starting a business making replacement airplane parts because we have FAA approved materials. On the right there, I believe that is some sort of electrical enclosure. Okay. So before we get into it a whole lot, I have a document for you guys. It's a white paper, an application brief, just kind of the Cliff Notes version of the presentation. It's not going to give you all the information that I'm going to talk to, but it's just a quick way to look and glance down and maybe have it for a later reading. Just a quick question: what is your lead time when manufacturing a newly designed product? Is it days, weeks, months, years? I just want to take this. I want to use this later on in the presentation, just to show you what we're spending, what time we're using. So we have years. I'm surprised by that number. Weeks and months is kind of where I thought we would be at, but years is pretty impressive.
Well, we might have some automotive people in here because it does take a few years to make a new car, and that's a newly designed product. But I'm sure we have some customers watching this where they might be just making single parts or small assemblies.
True.
Yeah.
Okay. All right, so a quick application overview. So what are end-use parts? So end-use parts are finished goods or sub-assemblies or part thereof throughout its life cycle. So I come from a production engineering background, so I wasn't involved with all of these life cycle terms. I didn't know what these were. Some of you may, some of you may not, but we'll cover them just in case. So we have pilot production. Pilot production is after design is done, we've released our designs, we haven't quite got the tooling in. We're setting up our shop, putting our cells out, and seeing how they're going to be moved around the shop, what machine they're going to go on, how they're going to be assembled, what nuts and bolts do we need to have in place. So once that's all figured out, we'll go into a bridge to production. Bridge to production is, we still don't have that tooling in-house, but we have a demand. We want to start manufacturing. So maybe we'll maybe tweak the design and make it something that we can manufacture and at least get a few units out the door. There's also a full-scale production. So our tooling's in our hand. We're all ready to go. All the assemblers are on their spot, and we're producing parts. And then at the end of the tooling life, where it doesn't become financially feasible to replace that tooling, we'll extend the life cycle by maybe making a few more, maybe at a premium, for people that need a replacement part, just for when that tooling is just not going to be replaced.
So do companies actually have to inventory stuff just for keeping extras laying around?
Quite possibly. Yes, definitely.
Gotcha.
All right. So up here on the screen I have, on the right-hand side, you can see a roll-around computer of some sort. This is in the medical industry. This company needed dozens of these. They didn't need mass production. All right. They needed, the dozens, so they had these printed. The housings on these are all out of a safe polycarbonate that is neutral to MRIs and CAT scans or whatever else they're using for. They're neutral and they can be used in this case. There's no link to company size types of products or markets for who's producing these. All right, plastic components are used everywhere. We have a picture there of, I believe that's a CAT scan machine. I had the unfortunate experience of going through one of those with my head one time. We have a little, very organic shaped, a little dragon on the right-hand side. I have a little bit more information on him later on. And then automotive. Some cars are almost completely out of plastic. I've actually saw a completely 3D printed car, if you have been watching the news, kind of how Todd was going over that. So where it's used, aerospace, automotive, motorsports, processing equipment, medical devices, you name it, people are producing stuff everywhere. Picture on the left is in the 900, I believe. So this is the biggest machine, the biggest FDM machine we have available currently. I'm not exactly sure what's going on in there, but they're producing something. On the right-hand side, we see a rim or a hub around a wheel. So this is on a semi. They needed one of these or two of these to replace these. These were printed on another 900, and they were sectioned together, and that truck is out driving along the road somewhere. An end-use part. So another quick question, and we'll capture all this data and use it later on, is how are you currently manufacturing your parts? Traditional manufacturing or traditional machining, so CNC or manual machining, some sort of molding, injection molding, RTV molding, what else is there, rim molding. Maybe you're 3D printing already, all right? Or are you not manufacturing anything, you're outsourcing? Or maybe you don't sell, maybe you're a service-oriented company. Wow, pretty overwhelming in the traditional CNC. I was hoping to see some molding. I was really hoping to see some printing out there to see people already doing that. So kind of surprised there, but I guess we got what we got. All right, so this is the process comparison. We're going to step through the process of traditional manufacturing. You guys, an overwhelming majority of you are going through this every single time. All right, so where does it start? It starts with a 3D CAD model. If you're using SolidWorks or any other CAD package, you're doing a 3D model. And we're in 3D printing, we can take advantage of the same model. All right, but we'll step into that later on. So we take that 3D model and we do a 2D drawing. Coming from a production engineering background, this is the part I despise. I hate making it and taking the time of putting all this information into 3D and then put it into 2D just so people in the shop could read it. Looking at this part, we have 3 different parts that are machined and then assembled. I've worked for a company where this wouldn't fly. Each part would need its own detail drawing, its own part number, and then an assembly drawing showing you how to put it together and calling out the nuts and bolts, having a bill of material. All right. So some traditional processes, you guys are very, very familiar with the CNC, the manuals. Each one requires a fixture setup. You have to cut a raw material. Cycle times are fairly high, hours. And then we have injection molding, where we need some sort of machined tooling or plastic mold. Very, very low cycle time. So we need to pump out thousands and thousands of parts to get the price per part down on the tooling. We also have RTV or rim molding. Rim is a reaction injection molding, which is using a curable resin as opposed to heat, warming up the plastic and melting it. So we need the pattern there as well. We're going to mold or cast, inject urethane of some sort. And for all of these, we need a skilled operator. So people go to school to learn how to do all this. Any change adds cost and time. If you want to add a feature, if you want to make an enhancement, it all adds time and cost. Let's go over the FDM process now. So we, as 3D Vision, represent Stratasys, and we have 2 technologies that we represent. The FDM side, which is the focus of this, and then the PolyJet side, which we will save for a later date. In FDM, we have 2 extrusion tips. All right, we have a model and a support tip. Any overhangs or internal passages will need support in there, and we dissolve that away with a water bath. All right, the model material is true engineering-grade thermoplastic. It's heated to a semi-molten state, and we draw a cross-section of our model, layer by layer. Now, doing it layer by layer, basically from the bottom up, or inside out, I like to say as well, is we don't have to build it solid. Right? We can do a sparse fill where we just have a very little amount of material in the middle just to hold it, to help it keep it shaped. So if you just need just a product mock-up, maybe on that first stage of production, where you're trying to set the flow through the shop, this is all you're going to need. You don't necessarily have to have it solid. Right? So the FDM process, it is an alternative process, but we can use it in all of those production stages, in pilot, bridge to production, full production, and end of life. Now, we don't have to do it everywhere. Well, maybe it works for us in pilot and bridge, maybe not so much in full, but definitely in end of life in the first two. It's good for production, or I'm sorry, custom configured products, products that change a lot. And the big thing is that there's no tooling required, and it's automated. After that 3D CAD file is done, before I've actually started that 2D file, that 2D CAD data, I can send it to my printer and have a part started. Right? So I'm going from prototype to production in one day. Talking about quantities, we're still not up to where we can mass produce a part. I mean, we want to be in the one-offs, maybe up to 1,000, maybe a little bit more. Probably a couple hundred is where we'd be most comfortable. And it's definitely linked to part size. We're not going to produce thousands of parts that are the entire build envelope of our printer. Some good parts where FDM is a good fit, or the best fit, is when we have frequent redesigns, continually enhancing our products, frequent stock items or revisions, lots of configured to order, one-off parts. Maybe we have some items that are optimization is desired, or we have complex designs, or we can design for performance. Over on the right-hand side, we have the dragon head, if we remember seeing that earlier. Anybody watch the show on, I think it was on Discovery, Orange County Choppers? It was a really good show, and they have one of our 3D printers out there. This dragon head was printed in Ultim. They had no other way to make this fast enough detail to get this motorcycle done. All right. Very, very cool looking bike. So FDM is also a best fit when the size is basically within our build envelope. Now here we say, about 1 cubic foot or less. Anything that fits within the build envelope can be done. And the FDM materials need to meet the specification and properties of our end-use parts, whether that's mechanical, electrical, or chemical. For thermal, we like to be below 390 degrees Fahrenheit, and as long as the tolerance, generally acceptable tolerance of plus or minus 5 thou. Now that plus or minus 5 thou is material to material and machine to machine, so we can hit tighter than that, like using ABS, for example, is a more dimensionally stable than Ultim. Okay. On the right-hand side, we have 2 more pictures of 2 other end-use parts. The top, the little girl, her name is Emma, and she has on her magic arms. If you go out to YouTube and you want a sad story, watch Emma and her magic arms. She was born with I don't know if it was a disease or whatnot, that she didn't have the strength to lift her arm up. She couldn't turn over on her own. And nobody wanted to manufacture a special vest for her. They have these for adults, but not for kids. They didn't, because they grow so fast. So it's something that changes all the time as she grows. So a doctor took it upon himself to make this little suit that she wears, and now with the rubber bands and the little strength she does, she can feed herself and she can play with her friends. A very sad story, but very cool ending. The bottom one is actually one of 3D Vision's customers. This is a military-grade drone.
So was that completely done in 3D printing?
I think the frame was not, but a lot of the housings and brackets and all that were, so part of it was. And definitely the prototype was. I think we actually have an article out there for one of their previous drones, which was more of a conventional airplane style. So very, very cool. Very, very cool. And good remembering. So other materials that we have available, looking at this chart, we have on the left-hand side moving across to the right and up. So as we go to the right and up, the chemical, thermal, and mechanical properties are increasing. So very far left, the weakest, least resistant to heat is our soluble supports. So these were good for maybe overmolding, maybe something that would dissolve away later on. We also have biocompatible. So we have materials that dissipate static electricity. And then on the far right is kind of our overall chart. We have the ABSs at the bottom, the stuff that your kids' Legos are made of. We go up into polycarbonate, nylon. Nylon was new last year or two. And then Ultem. Ultem has a higher tensile strength than aluminum and some other metals. We had a request from our last TechTalk for the actual spec sheet on our materials. So we have a white paper to hand out that has all of the FDM materials, what machines they run on, and the important specs that you guys want. The tensile strength, the HDT, everything you need. Okay. So where is this used? Well, we already mentioned Orange County choppers. We have ProDrive in the motorsports, ASYS medical systems and the medical devices, TDA in the aviation side, Minimizer. The picture that had the wheel well of the semi-truck, that was their product. All right, Minimizer. Novatech Engineering, we're going to talk about them in here in a little bit. And NASA. NASA is getting into using end-use parts. I remember when I was a little kid and we said, we're going to be in Mars, we're going to be going to Mars in our lifetime. And then what problems come with that? Well, you need to pack up everything you're going to need and a bunch of spare parts because you're going to have to wait two years to get something new. I mean, what if whatever device is producing the oxygen, producing the water, has a little widget that breaks on it? You have to wait 2 years to order the new one. Amazon doesn't deliver to Mars, as far as I know yet. So the answer is we just take a printer with us. NASA has a printer in-house. They have a satellite going up that's going to have components of it that are printed. I mean, they have a printer on the space station. They mailed a wrench to themselves. Okay, some benefits of FDM: time and cost savings. So we're saying that your lead time could be reduced by 75 to 90%. So most of us were in the weeks, maybe a couple months, and a few of you were at years, maybe in the automotive side, reducing it by 75 to 90%. Production starts as soon as that 3D CAD file is done. And we're reducing costs, mostly on the tooling side, 50 to 90%. Right? There's no upfront cost. And once the printer is owned, that's all there is. It becomes a streamlined, efficient process. We eliminate those detail drawings, which was a huge benefit to me because that's what I had to do. We minimize PO payment and payment requirements. I did some consulting at a company that from one department to another, one department had a 3D printer and another department didn't. And the department that didn't had to write a PO to the department that did to get something made. I mean, we're getting rid of all that payment requirements, all that paperwork. We're turning the manufacturing process into a task, not a long drawn-out project. And digital inventory. Todd had asked about the space involved and the money involved with storing all this equipment, with storing all the parts that we have. When our tooling dies, we have to have enough built up to replace that. Right? Simple duplication. When I send, it's as easy enough for me to send one part to a printer as it is to send a whole tray of parts to the printer. And we have design freedom. I mean, we're not designing for manufacturability anymore. Worrying about how big our chuck is, if our drill bit's long enough. I mean, I've drilled holes and I've sent parts to production where they weren't able to make them because I didn't design it with manufacturability in mind. Right? We can optimize performance, consolidate parts, eliminate assembly, reducing part count. We have lots of flexibility. We can change them as needed. We don't have to worry about retooling or modifying that tooling. And it's all automated, what we call lights out. You send that part, it's printed, it's there waiting for you the next morning. Okay. Wanted to get in, this last section is our customer success story and the benefits that they saw by going to FDM. Now, a little bit of background on Novatech Engineering is a fairly small company up in Minnesota. And what they are involved with is making equipment involved with the hatchery business. So you think about the chickens that, all the chicken meat at the grocery store, the Tyson and whatnot, they get their chickens from somewhere and they have to produce them fast. So Novatech isn't involved with the dirty side of that business. They're involved with the cute fuzzy side where we get the eggs, hatching those eggs, and we get the chick. All right. So if you think about all the birds that we want to be able to produce. I guess they're not really being produced, but they're being grown. If you think about all the different breeds out there, I mean, maybe not just the people that are growing the meat birds. Maybe they're people that want to bring back, produce bald eagles, or they want to release pheasants into the wild to restore some lost land. Right? These are the guys that are doing that. And for each different breed of bird requires a different tooling. All right. So one mold does all of the molded products on one of their machines. All right. Now, to get that mold done, and this picture on the right-hand side is just one of those parts for that family of basically tooling bits that work with the eggs, that roll them, that keep the humidity and temperature just right. 4 weeks to get that mold made at a cost of $44,000. It's a pretty substantial investment, especially when you think, well, we messed something up, we have to get it remade. Well, that's another 4 weeks, another 44 grand. Well, maybe it's simple enough that, well, it's cheaper, we can just rework it, but we're still waiting that 4 weeks to get it back. So they moved the production of this part of their machine, removed that tooling cost, FDM, 3 days, and $1,490. A savings of 25 days of production time and $42,000. 97% of their costs involved with this machine or with this set of tooling went away. Looking on the right, the top version was the molded product. So that was designed to be molded. We took advantage on the bottom of consolidating parts. Something that was very, very hard to mold. We were able to print it. We consolidated parts. And we took advantage of 3D printing, where we made certain areas sparse and certain areas solid to put the strength where we needed to and reduce the weight where we needed to.
So you're saying, Jeremy, by using 3D printing, we actually made a better part because of the process of manufacturing, right?
Absolutely.
Great. That's awesome. Good story.
Yep. And we have a white paper over on the side. There should be a link coming up about the Novotech story and the details if you want a copy of it. Go ahead and grab that. And I have one last question before we get going. What is your biggest obstacle for introducing 3D printing in your company? Whether it's upfront cost, plastics aren't strong enough for my application, the learning curve, or time investments too costly for you. Or maybe your way works, why change?
Another option on there is maybe people believe that their parts are too big and won't fit on a printer. And there are a lot of variety of different printers and size envelopes too. So maybe they just aren't aware that there's printers that can print fairly large parts.
Yeah, I mean, nobody knows they have that problem until they're shown that problem.
Yeah.
Okay, let's take a look at our results. Upfront costs. So this was our number one response in our last Tech Talk regarding 3D printing. And I talked to Ginger, one of our account managers for this, and asked her how I should respond to this issue. So there's lots of financing options. Stratasys will do 0% financing. There's lease-to-own options where for a couple $100 a month over a number of years, we can have a printer paid for and you own it at the end of the lease. And then think about those times. If you're spending weeks and weeks and weeks on tooling and getting ready for your production, what is that time worth to you? Plastics aren't strong enough, and the learning curve and time investment. I challenge you guys to reach out to me. I want to see what's going on, if you don't mind. The learning curve and time investment. So if you got 3D CAD, you can print. It's as easy as opening a Word document and saying print. It's the same thing. I'm opening up that file in my program and I'm hitting print.
Hey, Jeremy, is there a whole new way of designing if you're going to 3D print, or is it just a slight modification to your part, or do you even need to change your model at all?
Well, the short answer is it depends. It depends on how you want to use your printer. If you want to get the most out of it, yeah, we would want to change the design a little bit. So all those weird angles we would put in, like all the draft we'd put into injection molding to make it injection moldable, we could get rid of all that, make the walls straight up and down. We have stuff called self-supporting angle where we don't need the support structure. We can get it, we can kind of trick it and not use it. We can do the sparse fills, putting solid areas, make them solid, make sparse areas sparse to reduce the weight in certain areas or make it more ergonomic, something that we couldn't traditionally manufacture. We can make it printable.
But it doesn't sound too difficult, and that's really where your expertise comes in.
That's my job. That's why I'm here.
Okay. Everyone in the audience, if you're unsure still and you want to test to see if your part might be a viable candidate for 3D printing and end-use parts, contact 3D Vision at our website or the numbers shown on the screen.